Ladies and gentlemen, I have the pleasure to introduce you our running project, Move2Grid. As you can see, it is a 2 years project, and I would say it's pretty hard to condense everything down to 8 minutes. I will do my best. Here on these slides, you can see also the project partners involved in this project. Some of them are also here in this room. Overall research question in the project is the question how local renewable resources can be used for the local support of electric mobility in a long-term goal, and how this mobility can be integrated in the distribution grids in good technical and economical sense. And the initial situation, as we see it mostly today, is that there is various fields of actions, mobility simulation, grid planning, and also business planning, business cases, which can be seen today mostly as separated fields. And our approach actually was that the overall question can only be answered when the fields be answered in a combined and coordinated way. So our goal, the high-level research target is to find a way how the local use of local renewables can be maximized, how the implementation into the distribution grid can be done optimally, and how the locally achieved added value can be maximized. So at the end of the project, we do not want to have those separate fields. We want to have this integrated layer model as stated above. The methodology is that we want to do this interdisciplinary research in a top-down way. We want first to combine aspects from mobility planning with aspects from grid planning. Then we want to connect these technical results with research coming from business planning. And this is also one of the outstanding things in this project. We want to do everything based on real-life data coming from a fleet test, which is running all the time during the project. So we all are using electromobilities just to generate data that we use directly in the project. The first thing we had to do was to model real-life EV load profiles. We do this together with the mobility planning partner Verkehr Plus. The difficulty in the determination of EV load profiles is that different user groups act differently. We consider various user groups. Some of them are stated up there. The first data that we generated was user group based data from traffic analysis. So the guys from mobility planning, they were really going out counting cars for the various user groups. This user group based data was then combined with data from mobility, how far the various distances the different user groups were driving are, and out of these two numbers, it was possible to calculate EV load profiles. Those EV load profiles were the basis for grid planning. This is actually the part my institute is doing together with Energienetze Steiermark, and we do grid planning on 2 levels. We do it in the low voltage grids and also in the medium voltage grids. What I show you here today is only an example of a work package which is already finished. We have here results from the low voltage grid. This is a standard urban low voltage grid system on a 630 kilovolt ampere transformator. Very, very standard conditions. And our plan was to see or to calculate the influence of electromobility and PV on this grid. We have, of course, generated lots and lots of results, and I will show you some, in my opinion, outstanding figures. This is the result for a, I would say, rather low EV penetration rate. 20% of the cars were exchanged into electromobility. And what you see here is that there is problems in the grid, and these problems occur when all the cars, single phase charging cars, charging on the phase L1. This is actually what is happening today because we don't have any regulation that EVs have to be distributed equally in the grid. So you see there is a huge unbalance in the grid happening. When we change charging to equally distributed charging, then you see that this unbalance problem is no longer here, even in the case when we have an EV penetration of 60%. This was actually also for us a quite astonishing result, that the grids are relatively fit also for high penetration rate, not the grids, this exact grid, which is a standard grid for urban situations. At the moment, we are trying out other grid situations as well, and we see, very similar results. Conclusion. The integration of EVs into urban low voltage grids seem to be possible as long as charging power is low enough. What we are doing here is 3.7 kilowatts symmetrical charging. And conclusion number 2, and this is actually the link to the business cases part. Probably some customers need higher powers sometimes, probably when they have a Tesla at home and they want to drive from Leoben to Vienna or something similar. This is actually a perfect basis for new business cases, and this is also one of the business model options. The colleagues dealing with that are taking into account, number 1, demand-side management tariffs, so grid supporting charges at home. For instance, this situation is one of the the colleagues are taking care about. Second option the colleagues are working on is the so-called power bank situation, where self-produced PV power is used for charging EVs at work. But since this is a running project, we don't have any real results for that. I'm sorry. I can present this in one of the next presentations probably. So this brings me then to the conclusion of my very short talk. Mobility planning is the necessary database for real life load profiles needed for real life EV planning. So the conclusion here is that when we are talking about sector coupling research, then we need to have also interdisciplinary research. Conclusion number 2, the prevention of critical imbalances require free-phase charging technologies for future EVs. As long free-phase charging is guaranteed and the power of charging is not too high, we found out that relatively high penetration rates seem to be uncritical. What we have investigated was only an urban standard grid. This one has to be taken into account. Future e-mobility can act as a new driver for new business models, and what we find as very interesting is tariffs dealing exactly with changes in power when cars are charged. And this leads me to my outlook. Some or a lot of more results will be provided by the final report. More details concerning renewables and EVs, more about EV integration into medium voltage grids, more about regio-economic effects. Thanks for your attention.